you hear me? Is it fine? Okay, cool. Again, sorry for being late. It's not entirely my fault. I could have booked a train, so that bit was my fault. But yeah, so the first thing I'd like to ask you folks before I start is, normally I spend the first half an hour to 45 minutes of this tutorial just helping people set up their environment because they can go back home and then do their own text analysis stuff. Now, there's two things. One thing is the internet is kind of iffy. That's the first bit. The second bit is, since I'm also late to save time, would you want me to skip this part of actually setting up all the environments? I have all the instructions, on the GitHub link, which I suppose you should have all got. If you don't have it, let me know, and I actually can't help you find it because my internet isn't working, but we can somehow find it. So do you want me to spend this time in setting up the environment and doing all that stuff? Because honestly, it would be really useful for later. But if you're not super hot about that, then we can just go ahead with the fun stuff. If you want to, then just a show of hands. How many people want to spend half an hour setting up environments? Yay. No one? Okay, cool. This makes things easy. Okay, wonderful. Though I do want to make it a point that it's actually the reason I spend so much time in all of my tutorials and setting up this stuff for half an hour is. Come on, don't die, don't die, don't. That's also why, but I suppose. Okay, I'm still going to continue talking. Is because the environment which I suggest or ask people to use is right now the state of the art in natural language processing, text analysis, and computational linguistics. So it would be really useful if you had this particular stack on your personal computers. You will be able to find all these requirements on my personal GitHub page, which is my name, Bhargav, B-H-A-R. Oh, thank you. So it's on GitHub, and then it's Vader, like Darth Vader. I was really young when I made that. And then go to personal, and you should be able to find notebooks, text analysis tutorial, and you should be able to find particular notebook. So is that okay with everyone? It would be really nice if everyone was kind of on the GitHub page if they had the internet. Yeah? I'm sorry? Come on? Oh, zoom in. Can I zoom in? Oh, okay, I can. There we go. So, I'm sorry, is everything okay? Yeah? Okay. A little more, okay. Hold on. Yeah, okay. It's Command Plus, is it now? Thank you. I did not know that. Okay. So it would be nice if everyone is on the GitHub page so you would know what tools we will be using. And there's a particular reason is because most days if you just search up text analysis in Python, you normally get an NLTK link. And you have a lot of examples with NLTK. NLTK is a Python library called Natural Language Toolkit, I suppose. And I'm going to be talking about how we don't want to use that. We really, really do not want to use NLTK. It's old, broken academic code. If you want to test something out, it's okay, it's fine. But if you really want to do any cool, funky stuff, no, NLTK is not what you'll be doing. It has a bunch of different tools where you can try out different things. But it's not really what we're interested in as data science practitioners. If you want to learn a little bit, yeah, you can Google that stuff on your own. But NLTK is the opposite of what we'll be doing. Instead, I'll be focusing on some libraries which are more efficient, at least libraries which actual people are using in production. The main library which I'll be talking about is called Spacy. Spacy is a computational linguistics library in particular, and I think there should be links later around here or on my GitHub page. But Spacy is a library which I will particularly want to introduce, and after that we'll be using three Python libraries which are used a lot in machine learning for text. One is GenSim, which is used for topic modeling, which is why it's called a topic modeling tutorial, tips and tricks in topic modeling. You'll have scikit-learn, which I suppose most people here, everyone knows about. And you have Keras, which is used for deep learning. A few things before I actually get started. This is not a tutorial where we'll be going in depth. It's a breadth tutorial. So we're just going to kind of be exploring different possible things you can do with text, rather than looking at one particular method and going deep into that. I used to normally have a tutorial. I used to work specifically on topic modeling. And that tutorial is on the same directory this one's on. So after we're done with this, if you'd want to, you can go back and check for more details on topic modeling in particular. And I've kind of littered my entire library, and I mean this entire repository on GitHub with a lot of useful links and other notebooks and things like this. So do like start it and like make sure you know where it is so it's useful for you folks later. Yeah? Okay, so now we can get started. Unfortunately, I don't have this over here, so I have to also be looking at that, which is kind of annoying. Yeah, so what we're going to be doing is first, what I wanted to do was actually walk you also through the data collection part of text analysis, which is also an important part of it. For example, if you're scraping data off the internet, of Twitter, because it's a lot of fun, because Donald Trump tweets so much, and it's just fun to look at what he's talking about. And of course, there's Reddit. I spend way too much time on Reddit, and it's really interesting because you can, there's a lot of textual data which is structured really well. If you've been on Reddit, it's a forum for question answering, kind of. I mean, there's lots of threads, and you can see who's replied to whom, and so on and so forth, and this comes in nice JSON files which you can download. So websites like this are particularly useful for text analysis because it's structured data with replies and conversations. I like Reddit more than Twitter, for example, because there's the language is better depending on which subreddit you're on, but more or less, Reddit seems to be a more cohesive source. There's a lot of online sources which are very, very interesting. Unfortunately, we will not be doing that because I found out when I was actually figuring out how to scrape data, that's an hour and a half on its own. So we're going to be skipping the part where we're going to be scraping data and going to when we're actually having our data. So if we're going to be doing that, that means, okay, first I'm going to start with my imports. If anyone else, it would be really awesome if you all had all these libraries and a Jupyter Notebook running so you could be pressing the cells with me. But if you don't, then you're just going to be watching me press the cells, which is also fairly exciting, I suppose. Yeah, and that's imports. And we're using Theano. So Keras runs on both Theano and TensorFlow. I think the default here is Theano for me at least. This is in Python 3, this notebook. And yeah, these are some other imports for Matplotlib. The section on gathering data, I've just written down some of the things which I told you, which is about the whole Twitter collection part. And so this is the important part. Since we're not going to be using data which we collected online, I'm going to be using two data sets throughout this tutorial, which are already available on some of the libraries we're going to be using. A lot of libraries do this. For example, Keras has the IMDb sentiment analysis data set preloaded. GenSim has the Lee corpus, which is just newspaper articles over, I think, a year in Australia. And scikit-learn has the 20ng data set, which is, again, newspaper articles. So a lot of machine learning libraries have pre-processed, kind of pre-processed textual data sets on their, in their code base. So the first one which you'll be using is the Lee background corpus. Just a little bit of background about this corpus. It's, I believe, 300 articles from the years 2000 to 2001 by an Australian news agency. So the context is more Australian, but it's generic news. And this is the data set which we'll be first using to kind of start and get a feel of what we'll be doing. Before I actually get into the meatier stuff, are there any questions in particular, anything you want to know? Please feel free to stop me while I'm talking. Raise your hand if you have any problem, especially with the code, because I'm going to try and walk you through every single line of it, but please tell me if something is not clear. Yeah? Okay, cool. So now I'm going to be loading the data here. This is just a bunch of OS stuff to make sure that we're at the GenSim path to pick up our data. And now we're going to start with the cleaning part. I'm going to talk a little bit here more about what I said before, which is about NLTK and Spacey, and also about cleaning data in general. Of course, in any kind of data analysis problem, or you're going to be dealing with messy data. That's how things are. And in some cases, cleaning or not cleaning it will make big difference. But in text analysis, it makes a really, really big difference, especially depending on what kind of task you want to do. I'll give you an example. Let's assume that you want to generate text. If you want to generate text, which is just for example, if you want to mimic how Shakespeare writes or something, then you're going to want to not strip away any parts of the original data because you want to capture the way Shakespeare used his articles, used his nouns. Every single bit of the way Shakespeare wrote is relevant if you want to generate textual data, which is like what Shakespeare wrote like. But let's say instead you want to do topic modeling, which is a technique where we find out the key topics in a large body of text. we won't care about some words like the, and these are called stop words normally in natural language processing. Stop words are words which don't add any particular extra information to the corpus. For example, like the three words I said, articles are usually stop words. Words like same, go, here, there, these are all stop words, which are not necessary. So in your results, if you want to see stop words, in the case of Shakespeare, then you wouldn't get rid of your stop words. But if you don't want to see stop words in your final analysis, yeah, you're going to be wanting to get rid of them. So my point is cleaning data, knowing what kind of results to expect, and knowing what you want to see is really important before we start. In our first few examples, we will be getting rid of stop words because we will be working on topic modeling. So I'm going to show you a little bit about how we're going to be doing this with spaCy. A little bit more about spaCy and why I particularly really enjoy using spaCy. Well, firstly, so the way spaCy works is they have what they call a pipeline. Now, when you pass text through this pipeline, it annotates the text. When I use the word annotate means to mark or label it. For example, when you mark your classes, like class 1, 2, 3, that's also called annotating. But maybe a more, so before you pass your text into the pipeline, spaCy doesn't know what your classes are or anything like that. What spaCy does know is the English language, if we're going to be using the English language model. spaCy also has German, Italian, Dutch, French, and a couple more ones coming up as well. Really active young community doing a lot of fun stuff. So there should be more languages, but we'll be focusing on English. And so what spaCy does in its English language model is it starts to annotate and tag your text. It starts with first tokenizing. Tokenizing here means it's going to break up, for example, if it's I went to the bar, it would break up I went to the bar as 5 different words. And usually it figures this out using white spaces, which is your spaces between your words. Now, spaCy is intelligent. It's not only using white spaces, it knows how to pick out sentences, how to pick out words, and so on and so forth. It does most of the stuff using a neural network, and they've really fine-trained these models. Also, when you download these models, you have to first choose which model you want, trained on what kind of data. So now, you have your basic tokenizing, but spaCy does a lot more. It also figures out parts of speech, like nouns and verbs, and so on and so forth. And it goes one step further. It picks out something called named entities. Named entities are things like organizations. For example, Go Data Driven is an entity. PyData Amsterdam is an entity. Amsterdam is a geopolitical unit. Then you have places, so it marks different things which are, for example, an apple is not an entity, but the company Apple is an entity. And these are called named entities. It also picks out something called, in sentence structures, when we parse a sentence, we can dependency parse it. What does this mean? Actually, you're going to see an example which would make things easier, but you get the gist of it. spaCy does a lot of really cool, computationally linguistic, intensive stuff in one pipeline. Now, apart from things like parts of speech tag and your named entities, why is this interesting for cleaning our text? It also points out what stop words are, which words are stop words, which words are numbers, which words are punctuation. This means when we're creating our corpus is the data which we actually want to create and give to our machine learning algorithm. When we're creating our corpus, we can get rid of numbers if we don't think they're important. We can get rid of stop words. We can get rid of pretty much anything and everything we want to and keep what we want to using spaCy's pipelines, which have now annotated our text. Is that clear? Because this is very important. This is something which, for example, NLTK does not do. In NLTK, if you wanted all of this, you would have to write code which removes stop words manually, just like you get a massive list of stop words. You check your list if the word is in stop word, remove word from list, and so on and so forth. I mean, yeah, we can write the code, but the whole point is we don't want to waste time writing this code, which we write every single time when we do text analysis. Same with numbers. You can, of course, have a list of numbers and say, get rid of numbers. But spaCy is really neat because it does all of this boring hard work for you. And it does it extremely easily, in fact, in just this one line of code. So when I do NLP is equal to spaCy.load en. En is the link to the English model, which I talked about before, which you would have downloaded if I came earlier. When we do spaCy.load, we're loading this English language model into NLP, which is our variable storing the model, and this is a pipeline. So NLP now is our pipeline. The next cell, Jupyter cell, so I include the cell over here to give a small anecdote about natural language processing in general. So this corpus, like I mentioned before, was a corpus with newspaper articles, yeah? And when I was trying to find my topic models using this pipeline, the word say and different forms of say, like saying, said, and so on, they were not counted as stop words. But you can imagine in a newspaper article, there's going to be a lot of people saying say, said, so on and so forth. So when I was getting my topic modeling results, I didn't really need the word say in it, and say just kept coming up really, really high in my list. So I manually added these words to my list of stop words. Why do I mention this is that in any, I mean, of course you do this in every machine learning task, but particularly in text analysis, you're sometimes expecting a certain kind of result. So sometimes you have to look at a results and say, okay, this doesn't make sense. Go back and restart our entire process until we get results which we kind of want it to look like. This may seem counterintuitive, but then because of the fact that these are more exploratory algorithms we're going to be looking at, like they're going to make you explore your text, you know, not classify or cluster, this is useful. So you should kind of run your results once, look at your results and say, okay, I don't want my results to look like this, and then make small changes to make sure results look a little, or make more sense. So, I mean, in this particular example, the word say didn't have any, it wasn't supposed to be in my final topic model, so I've added this to my list of stop words. The way spaCy identifies stop words is every lexeme is just another, it's a class in spaCy which stores the word, and it stores certain characteristics of words. So here we're forcing these words to be stop words for this particular example. This small loop runs us through it. If you want to add more words, just add more words to that list. Now, I talked about running your text through your pipeline, yeah? This particular cell you see over here, oh, it's much easier if I look at this one. So this particular cell over here is actually the cell doing most of the heavy lifting in this one line of code, and it's going to take some time to run because it's not tiny. But this is 300 articles. Now, doc contains, I mean, so text was our initial text, which we loaded from, where is it? Over here. This is our text, and then we're running doc is equal to NLP of text. So we're passing our text through our natural language processing pipeline. I talked about how the moment we're doing this, now spaCy has a lot of information about every single word, every single token in all your documents. So let's look at what exactly doc. So this is it. This is every single one of our documents. It looks exactly the way, I mean, it's unprocessed. You're not going to see any tags because it's just plain Unicode text. You can see, it's just basically our documents over here. But what's happened under the hood is spaCy has annotated every single one of the tokens over there. So hundreds of people, every single one of these tokens have been annotated with lots of different kind of information. So now let's start with, yeah? Oh, like punctuation marks and numbers are also tokens.
Okay, but for example, south of the Kashmiri summer,
I'm sorry, I'm just going up there. Yeah?
This is not one. This can't be one token. One token is always one word.
Yes.
Okay.
Yes. And like the way, so you can actually train spaCy's tokenizer of how you want it to make tokens. For example, you can see this word, like it says night long encounter in southern Kashmir, like night long. So normally spaCy breaks this into night, and then the what's that thing called again? The hyphen and long. So you have 3 different tokens, but then you can actually train spaCy's tokenizer telling that if you want to catch all hyphenated words as one token, that's possible as well. So spaCy's kind of flexible about the way it does this because it trains, it identifies these tokens by using machine learning algorithms again and some rules as well. You can modify these rules if you want to for your particular task. But normally those will be 3 different tokens. So now, I wanted to show you that you can, yeah?
In terms of cleaning the data, does spaCy also do lemmatization or staring orders?
Most definitely. That's the fun part now, isn't it? We'll be getting there in a small bit. Spoiler alert. But yeah, so what's going to be happening here is the previous example, I showed you the entire document being processed by the NLP pipeline, yeah? Now, it's kind of difficult for me to show you particular examples, so I'm going to just use a smaller sentence over here. Which is this, so you would have noticed I'm doing pretty much the exact same thing. I mean, the above part I did doc is equal to NLP of text, but I don't want to show you the entire document being processed because it takes time and I'm lazy. So I'm going to show you just the sent. So basically whatever Spacey did to the massive set of documents, it also is going to do to the sentence. It's just easier for me to show you, yeah? So I'm going to show you some of the first things which Spacey does. And this particular part, I mean, just to be pedantic, this is called computational linguistics, because these are all traditionally, these are all tasks we do when we're studying linguistics. And since we're making a computer do this particular part is technically called computational linguistics, which is kind of different from natural language processing, which is more statistical, machine learning kind of stuff. But these terms tend to overlap. But just to be correct, I suppose. And yeah, we're going to start with pause tagging. And so pause tagging stands for part of speech tagging, yeah? And you can actually, so of course in different languages you have different kinds of parts of speech, and Spacey has different language models for different languages, and even for the same language you have, for example, an English language model trained on medical documents on particular domains if you'd like. But parts of speech tend to stay the same across, in the same language even across different domains. So parts of speech, at least in English, are like noun, verb, proposition, and so on. And you're going to now look at, so how you do it over here is for token in sent, which is for every single token in my sentence, which has been processed by the pipeline, I'm going to be printing the text, the pause, and the text. So I'm going to just show you what this looks like. So over here you can see that Tom proposition, proper noun, and then NNP. So here, NNP stands for the exact tag. So even when you have your broad parts of speech, which I believe there's 9 parts of speech in English. And correct me if I'm wrong here. I'm not a linguistics expert, but I do believe it's 9 parts of speech. And then after that, you can kind of focus in on more on which particular tag it is in that kind of part of speech. So what you can do over here is this is a super easy way for you to just print out every single part of speech of every single word. Now, why is this interesting or relevant? For example, I did a small experiment to find out what adjectives were used to describe Harry in the Harry Potter series the most in the entire book, which is really interesting because I just had to, so I got my sentences and then I tried to find out in which particular case is there an adjective for Harry in that sentence and noun, and then I check my list of adjectives and then I just count them and I have all the adjectives used to describe Harry now. So you can see how this kind of information, depending on the task you might want to accomplish, could be kind of useful. You might want to make a topic model which only has the verbs in all these sentences, in which case, when you're cleaning your corpus, get rid of anything which is in a verb. So, for example, you would be doing if token.pos is equal to verb included in corpus. You see? So you can use this kind of information in really cool ways, depending if you care about it. Now, in normal machine learning statistical kind of problems, we don't care so much about the part of speech, but it's still interesting information to have. Another thing to note is that you can turn on or off different parts of the Spacey pipeline. If my internet was connected, I would have shown you the different components, but so I do believe it's tensorizing, which is something which they do for their internal, making sure it's in the right data structure. Then it's tokenizing, part of speech tagging, named entity recognition, and then dependency parsing, and so on and so forth. There's 5 or 6 different parts of their pipeline, and each part takes different time. So if you only want to know about stop words and someone asks me a question about lemmatizing, you don't need the part of speech or the NER tags. So if you're running some code in production and you don't need this, you can turn them off. I usually include them because I think it's useful information to have, and it just takes a couple of seconds more. But this is just to give you an example of the kind of things you can do with Spacey's pipeline. We'll be now moving on to NER tagging. I talked about NERs before. NERs it stands for named entity recognition. And over here, again, so there's different kinds. So over here, there's only one entity, which is Tom. So you don't really have much. I probably should have written a better example in hindsight. But for example, if I had Tom ran to IKEA to fix his bicycle, even though it's a bad idea, but you would still have IKEA as an organization over there. So there's different kinds of named entities. You have geopolitical units, you have people, you have companies, you have, for example, you have also places like, you have countries which would be, like Amsterdam, Netherlands, and so on and so forth, but you'd also have things like mountains, and so like the Carpathian Mountains for the Carpathian Basin would be a different entity. So you have different kinds of entities which you can capture over here and use. again, if any of you are connected to the internet, I would really recommend just Googling Spacey NER tags to look at the entire list of it. I cannot bring it up right now. But in this case, Tom is a person, so he's tagged as a person. Just one thing to point out, for here, we did for token in sent, and then we went through every single token. What Spacey also does is it also just picks up your entities, yeah? So in that case, you'd go to for ent in sent.ents, which means for entity in the sentences entities. Sentences, yeah, that sounds right. So Tom's the only entity in the sentence, so you'd only have Tom and person next to it. Now, pardon me. The other cool thing which Spacey does, and this is really neat because they have this with Jupyter Notebooks, they have a nice interactive way to look at your named entities, which is called Displacey. Here it's not so pretty because it's only, again, one entity, but I swear it's a lot prettier if there's a lot of entities. So if you could like write up a sentence with a lot of entities, you can try it out yourself. You know what? Heck, I'll just do it myself. I should stop. Okay, Tom. Okay, Tom went to IKEA to get some of those delicious Swedish meatballs. Yeah? Is there a spelling mistake there? I can't really see. Okay, either way, Spacey should catch this. So in this particular case, come on, where are you? Yeah, there you go. Did they mess up Swedish? Oh, they did. So it's, oh, perfect. So don't you know what exactly goes on? Yeah, so you catch his entities and you can display these entities in a pretty way if you want to. You can also go to the website Displacey and check it out. They have a web app. But this is just a way they've hooked it up with their Jupyter Notebooks. So now dependency parsing, which is the last part. So dependency parsing is a technique in computational linguistics where you can find out the structure of your sentence and look at the dependencies each word has with others. That's why it's called dependency parsing. You're going to get a good example once I print these things. This is not, so these two are not as useful right now, but when you see this, it's a bit more useful. Where's my damn mouse? Yeah, so what's happening over here is normally in dependency parsing, the root word is the verb. So here went is the verb, and the entire sentence, so Tom, so you'd have to study linguistics here to make more particular sense out of this particular example, but it tells you normally you have the subject and the object in sentences, and it breaks your sentence up into your subject and object, and it kind of tells you how different words are related to each other in a sentence. Over here, now, in my opinion, my work so far with Spacey, these are not super useful. I prefer, I mean, it depends on what kind of relations you're actually looking for between the words. For example, if you're looking at, again, which word, who is the subject and who's the most common subject in these cases, there's certain ways to find this out. So Spacey has, again, on Spacey's dependency parsing documentation, they go into more details about the more practical applications of dependency parsing, but I'm going to give you one example. When you talk about dependencies in this particular case, it's linguistic dependencies. But Spacey also gives you the ability to create your own dependencies. For example, if you want to consider a dependency as how you describe something, or like an adjective, like for example, in terms of how close it is to something in proximity, like near and far, you can create dependencies by giving examples of the shop is close to the station, and then close and station, you train Spacey telling Spacey that the word here close means the shop is close to the station. You can actually create dependencies for Spacey to learn and then use this new dependency scheme for the rest of your tasks. On the website, you can actually, this is quite a big section because they use deep learning to train these dependencies. But if these kind of things are interesting for you, I'd really recommend checking it out. But as for the vanilla stuff, this is still pretty neat, right? But yeah, so now this is just to give you an example. So whatever's happened here with the sentence has also happened with doc, the entire massive corpus. Let's not forget the Australian newspaper articles we were talking about before. So this is an example of what Spacey does. When we ran our sentence or document through the Spacey processing pipeline, we not only had access, like I said before, to all our stop words and all our lemmatizing and things like this, we also have access to these kind of neat stuff. But this is just like a small detour to give you a taste of what you can do with Spacey. What we're actually going to be using Spacey for is for cleaning our text. So let's look at this. Do I need to zoom in for you folks as well, or is this okay? It's okay? Okay. So we're gonna now create our corpus. A corpus is just a word to like in natural language processing. It's a word we use to describe our collection of documents. Yeah. So most like Jensen, for example, and even scikit-learn, it does not accept just words. I mean, obviously, computers can make sense of words. What we need to give them is numbers to represent these words. So there's different ways we can do this. A popular way is bag of words, where we pretty much just count how many times a particular word appears in a document. You create a dictionary. Okay, first you create a dictionary which maps every single word to an ID, and then you read your document. You see how many times that IDs occurred in the document, which means how many times that words appeared in that document, and then you just add that up. So it's like a bag of words. This is one popular way. Another popular way is TF-IDF, which stands for term frequency inverse document frequency. Term frequency means the number of times that term appears in a document. Inverse document frequency is how is it distributed among all the other documents. So these are just different ways for the computer to better understand what words are in our documents. Yeah? So we have to first create this. This is an extremely, extremely important part of text processing, creating our corpus and cleaning our text. So this is how we're going to be doing it in this particular cell. Now, this is extreme. That was really fast, nice. So this is really, really important. Let's first look at what exactly text looks like. Text is a list of lists, yeah? And it's a list of lists where so the massive list, I mean the outer list is your entire corpus, and each individual list inside is your individual document. I mentioned before there are 300 documents, so the length of texts, which we can quickly verify, should be 300. Please be 300. Oh, damn. Of course it had to be 299, but you get the point. I mean, it's... so text contains all our, each of our documents. Now, how did we go from here to here? Let's look at this with a little more detail. So I did for W in doc. Doc is my entire document, which is processed by Spacey. Let's not forget that. And W is each single token or word. So I first look at this. If it's not a new line, because if I go back and look at my document, I can see that every new line's the end of one particular article, yeah? So I'd want to kind of have a different list for every article, so I want to make sure it's not a new line. If it's not a stop word, so stop is the attribute which tells us if it's a stop word or not, then if it's not punctuation and if it's not a number, then I want to use this word. Yeah? So Spacey's given me all of this information in one swoop, along with the whole parts of speech tag and a neon and everything. So we had all this information, and now what I'm going to do is append the lemma to the article. So this is the question you asked me about, does Spacey also have things like the lemmatized form of the word? And the answer is yes, it does. Now, what exactly is lemmatization? For example, in topic models in particular, this is interesting because say we have say, said, saying, and says. These are 4 different words. But it's not really important if it's more useful for us to know what this word implies, which is the root word say, rather than having these 4 individual words. For example, imagine we had a final topic or document which just had say, said, says, for example, so on and so forth. Like, this is not useful information to me. It's more useful if I just have the root word. So a way to find out this root word is lemmatization. There's another way called, there's another method called stemming, which we'll not be using. These are just different ways to go about doing it. Lemmatizing, so a lemma is basically the root form of the word. So in this particular case, I only want to add the root word. I don't care about, is this clear? Do you understand why I'd want to do this and so on and so forth? It's also, let me make it very clear, it's very, very neat that Spacey does this for us. I cannot stress this enough. We're doing, in this tiny loop over here, we are literally building our corpus, which will take a lot more time with NLTK or doing things on our own, yeah? Spacey's making us do things really, really fast over here. And after that, since when I see a new line, I know it's a new document, so I make my list empty again. I append that article to my massive corpus, and I go on. So these 2 cells are actually extremely, extremely important. They're probably your biggest takeaways from this. Don't be disappointed by that. But I'm not kidding, though. It's really, really important. Making your corpus is an extremely important part of text analysis, and making your corpus like this is also extremely, extremely important. So is that clear? Is everyone on board with me up till now? Awesome. Okay, so I'm going to now use so I'm going to just now describe a few things we're going to use which are more GenSim specific. We're going to be using our first GenSim module, which is bigram. Bigrams are collocations. Collocations are bigrams. They're a really neat natural language processing trick. So these work on the idea that sometimes when some words appear in the context of other words, they might make more sense if they appear together. I think I've given an example of the word New York over here. So, for example, if we see in our body of text that the words New and York are appearing often enough for us to take it seriously, it's probably more useful for us to consider it as New York instead of New and York. Yeah. So what bigrams, so collocations are words which appear around each other, and we just do this in a probabilistic manner. We just look at how often words appear around each other, and we try and predict if this word is more useful as one word or not. Another example which you'll see, again, kind of spoilers, but in the topic modeling, is since it's in 2000 and 2001, Osama bin Laden is really, really relevant, and so is Al-Qaeda. So you'll see that when I first ran my topic model, I saw a topic model which is kind of like a terrorist topic, and it had like Al-Qaeda, Osama bin Laden, and so on and so forth. Again, this is like early 2000. So, but Al-Qaeda, Osama bin Laden were all different words, and I'm like, wait a second, this is not really cool now, is it? So I ran these, so I looked at my results, and I went back, I'm like, oh, let me use bigrams now. And I ran bigrams, and after I ran bigrams, my results actually had Al-Qaeda as one word and so on and so forth, which kind of saves up a word for me, you see? So it's a really, really neat trick, which I would recommend using if you want to do this kind of analysis. So, and by the way, you can also make trigrams, like, again, because Osama bin Laden is 3 words. If you want to make a trigram, you just run a bigram and then run another bigram on top of that. It's not real creative, but it's, that's how GenSim does it. And that's it. So when I'm doing text is equal to bigram of line for line in text, I'm recreating my original corpus, but now with bigrams. Yeah, is this clear? So now let's look at text of 10 to see if we find any bigrams. Come on, bigrams. Damn it. I should test this before I... Oh, awesome, New South. So you can see New South Wales was, is one particular case in this corpus. New South Wales, I think, is a state in Australia, though I reckon it is. So, which is why it's caught up. Maybe there's something else which also comes up. Blue Mountains, which is probably interesting. Maybe it's the name of the mountains nearby. So you can see how bigrams has caught words. Now, in the example of Blue Mountains, the reason it's caught Blue Mountains is because it's actually read the entire corpus enough times for it to think that, okay, Blue Mountains has come often enough together for us to consider it as one word. It would not consider it as one. For example, if you use the same bigram on a different corpus, it would probably not concatenate Green Mountains because it's not seen Green Mountains. It's seen Blue Mountains, so it's going to do this. Yeah? Okay, so now we're going to actually create our final corpus. I talked to you earlier about, yeah?
Does it also add the named entities in there without this corpus?
I'm not adding any, I'm not using any named entities information. But why exactly do you think it would be useful here? Oh, no. So when I'm creating my bigrams, I'm just using like basic conditional probability, trying to figure out what are the odds of this word appearing around this word. I'm not using any prior information if it's a political entity. Though I'm assuming, for example, if you were training a neural network, this might be useful information. But in this particular case, we can just go ahead with this. But also, just a note, the named entities that you mentioned were done by Spacey, and this is GenSim, which are different packages. So GenSim only uses like, just basic probability to figure stuff out, does not use any other information. So now I mentioned before that computers don't understand words, they only understand numbers. So now we're going to be first creating our dictionary. A dictionary is just mapping every word to an ID. So, okay, so now my corpus, I do dictionary.doc2bow. Doc2bow stands for document to bag of words. And now I have my bag of words. What does this look like? This is the 100 document. So it's basically said word ID number 14. I'm not sure which word that is, but it doesn't really matter now. It appears 3 times in this document, and so on and so forth. So if you really want to know what it is, just feel kind of guilty if I don't. Where are you? Okay. Yeah. So dictionary of 14 is the word in. Okay, that's boring. But well, the word in, the word in comes in that particular document 3 times. So that's what bag of words is. You see, it basically counts how many times a particular word's appearing in the document and goes around building it, stuff like that. So here we go. So at the end of corpus, we're actually done with our pre-processing. This is the most straightforward pre-processing, which is normally done in text processing. What we did was we got rid of numbers, we got rid of punctuation, we got rid of stop words, we added the lemmatized or the base form of the word, and this is all we did. We can get fun, we can do more creative things with this if you really want to, but it also depends on looking at your results and saying, oh, this looks bad, so I should probably process my text better, and then you go on, you go back, and then you look at it again, then you run the whole thing again. But this is the pre-processing which we're going to be doing. And we've set up our corpus, and we've used bigrams, and now we're going to do our first machine learning part, which is topic modeling. So I'm going to first briefly explain what topic models are. Okay, for example, let's say you have a bunch of newspaper articles, yeah? You work for a newspaper company, you have a bunch of newspaper articles, completely unstructured text. You have no labels, no categories, no dates, nothing. You just have 500, I can just make up numbers, 500,000 articles from the last 20 years, and you just have and your boss comes and tells you, organize this shit for me, and you have no idea what you want to do. So this is where topic modeling is particularly useful. It's because it helps us do an unsupervised modeling of your documents. What does this mean? This means we have no labels or no tags we're working with. We're just going to ask our algorithm to try and figure out what these topics, what these documents are about. Now, I gave you an example of newspaper articles. So what kind of topics will we be dealing with? Maybe politics, sport, weather, and finance, maybe, for example. So we expect these kind of topics to show up, but there could be more, there could be less. So intuitively, depending on the size of your corpus, you say 10 topics, yeah? So you think there's going to be 10 topics in this, and you want to kind of see with the broad overview what kind of 10 topics are here in my corpus. So what's going on under the hood, like I'm going to do a really like hand-wavy mathematics over here, is it assumes a distribution over, so when I mean distribution here, I'm talking about a probabilistic distribution over each document. So what it says is that each document is made from a bunch of topics, and each topic is made from a bunch of words. So for example, your sports topic might have words like football, basketball, Ajax, Europa League, Champions League, and so on and so forth. Now, the topic, the computer doesn't know that the topic is called the sports topic, you see? It's just going to say that this topic, ID number 3, has these words appearing in really high probability, which is why we call it a probability distribution. So it's going to say, topic ID number 4 have these words and these high probabilities. Then you're going to have another topic, say the sports, already talked about sports, the weather topic. And the weather topic, since it's Amsterdam, it's going to have rain, and more rain. But no, so you get the point, though. You get the gist. You're going to have different topics with different words appearing in different probabilities. The computer doesn't know what this topic is marked as. We're going to have to name these topics ourselves. But you're going to find so many words related to this topic, we're going to be able to do this. And you're going to have, in each topic, you're going to have different words appearing with different probabilities. So you're going to have 45% of the chances the word Europa is going to appear in football, and so on and so forth. And you're going to later have documents which are made out of topics. So it's going to probably say the first 30 documents are 80% football, and so on and so forth. If, for example, in some bizarre turn of events, Hillary Clinton is playing football in a really rainy stadium somewhere, you're going to have 30% politics, 30% sports, 30% weather. You see? So each document is made out of a bunch of topics. Each topic is made out of a bunch of words. What we're going to be doing now is creating your topic model is super easy. We've imported LDA model from Jensen. Jensen is the library which we'll be using for topic modeling, which is arguably the best topic modeling library out there right now, though scikit-learn also has topic modeling, but Jensen is kind of made for text, so it deals with the quirks of text analysis a little bit better. So here we go. Our only parameters which we're passing is the corpus, which is what we created. You saw the numbers, the bag of words. The number of topics, so in LDA, we need to mention how many topics we expect. As for finding out the right number of topics, really, it's impossible to say for sure what number of topics you're going to expect to find. Depends, you're going to have to run a bunch of tests and look out. there's a link over here which I've mentioned. I think I've mentioned it. But yeah, in the same directory, you're going to have my other topic modeling tutorial, which is a tutorial only for topic modeling. So if you want to get more into, for example, choosing your number of topics, there's a bunch of different topic models, choosing which topic model you want, and stuff like that. You can check out that different tutorial. But now I'm just going to show you really quickly LDA model. So it's training over there, and it's done. And I'm going to show you topics. So you can see over here that the word the and prawn, which I'm not sure what it is coming up very often in all of these, which means that it's a stop word which is not properly caught. So I would have had to go back and make sure I get rid of the, but I'm not going to do that right now. I want to finish the tutorial. But this is a good example of where not cleaning your data can lead to nonsense results. I did not plan this, but it's worked out well. You can still kind of see the topics, I suppose. For example, over here, topic 3, it says attack, group, Palestinian. Oh, things haven't changed. Things are still miserable. But yeah, you can see that in this particular example, this is kind of a topic to do with the Middle East. Then you have government, Australia, Australian, Afghanistan. So again, these are not very good topics. That's bothersome. So in this particular example, this means I probably want to go back to my original corpus, pick up the words which I don't like. For example, prawn might be something which spacey is thrown up, which doesn't make some sense. So I'd want to get rid of the prawn. Maybe day is not particularly important information to me. So I get rid of the word day, add that to my stop words list, and then I come back and then I look at these results again. So when you're looking at topic models, if you're not satisfied, and you're rarely satisfied with your first round of results which you get, you're supposed to go back, pick out the right stop words you want to get rid of, and you can see the LDA model I did, it got trained in around 3 or 4 seconds. It means that it didn't run through multiple rounds, it was just one pass. You can change this as well if you want a more fine-tuned topic model. I'm not going to be going through this particular part right now because I have a lot more to show you, but again, in the same directory, there's another topic modeling library, a topic modeling tutorial which I've written, which has the same exact corpus with a lot nicer looking results. So since we're doing this right now live and the stop words aren't cleaned so well, it looks a bit messy. But this still gives you an idea of what a topic looks like. You can see over there that 0.10 of 0 says that the word the has that's the probability of the word the appearing in topic 0. Normally that word should not be the, it should be something which makes more sense, but you get the gist of it, correct? About prawn, I'm honestly not sure. I think prawn was something that spacey spat out, and I think it's just a verb. So for example, if I'd want to get rid of this, just before in my corpus over here, I'd be looking at this and looking at, so I can see that still exists over here, at, and yeah, so you can see it's not been cleaned exactly the way I want to, because these words were not added to my stop word list, in which case I'd want to go back and do it. Just to give you an example of what the results might look like, is there... Yeah, topic modeling. This is my topic modeling tutorial, which I talked about before. I just want to give you an example of what nicer topic modeling. Come on, scroll for me. So, pardon me. Yeah. So do these look better? I cannot see. Oh yeah, this does, doesn't it? So this is the same corpus, but in a different tutorial notebook. So this is probably an example of better looking topics, I hope. Kind of. But this is, again, so you get the idea of how topics work. So I'm going to go back to the text analysis. Where are you? This is... Pardon me. There we are. Okay, so this is topic modeling. So we saw over here topics. As for your question about the and prawn, it's not supposed to be there. We're going to want to get rid of it in our text before we actually do it. So this is one part. So this is one example of the kind of things you can do using GenSim. GenSim has a bunch of other really cool stuff. One of my favorite text analysis techniques is word-to-vec. A lot of people have heard word-to-vec because it's, yeah?
What do I do with this output, actually? I see words.
Yes.
I see Australia. I see Palestinian.
Yes.
It's just words to me. Should I then, like, look for, like, how do I go from these?
Yeah, good question.
Of words to
Anything.
Topic that I could, for example, tell my girlfriend, yeah, in Australia, it's hot topic that company claims parties.
Yeah.
Something like so. Yeah.
Yeah, of course. Fair enough. So did everyone get that question? It was basically doesn't look very useful. How do I make this useful? Kind of. Yeah.
Yes.
Okay. So yeah. So again, I'd like to really mention that in this particular case, we need to go back and get rid of, for example, the word the, which you said first want to get rid of your stop words. So once you get rid of your stop words, and maybe you can run this with 2 passes instead of just 1 pass, or 50 if you have time to spare. So once you do that, I'm going to give the analogy of the newspaper example, the newspaper articles, for example. Once you have your topics, what you can possibly do with it is, apart from the idea that, say you didn't know what was in the corpus we were talking about, right? You had no idea what was in there. I mean, I told you folks that the Lee corpus has Australian newspaper articles from the years 2000, 2001. Now, if I didn't tell you that, and I told you we're just analyzing a corpus, and then I showed you these results, even though it's a really, really bad topic model, you still know that this is a topic, this corpus probably contains information about Australia, the government, things going on in the Middle East, so it's maybe Australian news, you know? So it's giving you a good overview of what's actually inside my entire corpus and all my documents without having to even read a single document. And this is with a bad topic model. Imagine the wonders you could do with a good topic model. So the other topic modeling tutorial, which will, again, like I've said, seen on this corpus, I talk about 3 other different kinds of topic models. Topic model coherence calculation, which is trying to find out the most coherent or meaningful topic model. So I've talked about measures for finding out. So coherence here is how human interpretable a topic model is. So you have ways to choose and fine-tune your topic model. And you can, so how it's useful? Usually in just explaining to people what's in my documents. That's probably the most popular way, because mind you, this is completely unstructured, unlabeled. I have no clue what I'm dealing with, and suddenly I have so much information. What you can also do now is, if you pick up every document, actually I can show you right now. This is easier. How do I, God damn it. How do I make a new cell? I can't see the top of my... Pardon me. Okay, so if I want... So this is to show you the topics. If I want to see what's the breakup of... for example, what I did over here was I passed... corpus 9, I mean corpus of 9 here is my 10th document to the LDA model. And now what I've got in return is what is the, so in this particular case, article number 10 is composed 98% of topic 0. So you can also now find out what is the percentage of each topic in all of my articles. Maybe this example is not telling us so much, so I don't know. Okay, this is kind of more interesting. So article number 89 is 25% topic 5 and 73% topic 7. You see? So this is the other kind of information and which we get. We can actually, every single one of our documents, we can classify we can't really classify because it's not a 0-1 thing over here, but we can get an idea what it's made out of. It's 75% this, 25% this. This can later, if you want to cluster, this is a way we can help in clustering as well. So there's a bunch of things we can do with topic models in general. You can also find out what is the topic of every single word in your document. And you can like color the words in your document to find out if it's a mix. So again, there's a lot of different, what you have to understand is topics made out of words, documents made out of topics and words. Words in each document belong to a topic, if you can kind of see where things are related. Using this information, we can do a lot of fun stuff with our topic models. So it's more of a data exploratory kind of thing, you know, which is why you don't have things like accuracy. You cannot test how well a topic model is. Like, for example, this topic model could make a lot of sense to someone, but not for me. So you'd want to retrain it and fine-tune it. Normally, it's used for another really popular example is in science, in general, like in research. Researchers like to find out what other researchers are doing research about. So you use topic modeling on all the papers written in computer science in the last 120 years to see what people are talking about, kind of arrange articles. You can use it to browse and find things. So in general, it's more of a data exploratory. I don't know what's going on, so I kind of want to have a look. And then if you want to get funky and do a little more stuff, you can do that too. But again, I give more examples of things you can do in my other tutorials. So I'd really recommend checking that out if this interests you. Yeah?
Is there a way to kind of force these topics a bit?
Yeah, you can seed them. So seeding, I mean, like seeding is used in a lot of things. I mean, for like, so the idea of seeding something is to kind of force or push your algorithm the right direction. So Gensim again has ways to do this in your, so you have look up the documentation for seeding your topic model, but you can say that you expect these topics to appear to kind of give it a head start and look for these topics. Okay, for example,
Do you know what the method is called?
it's just called seeding actually. Seeding your topic model. Yeah, it's pretty neat. Yeah, it is. And like Gensim, so Gensim has, I would really recommend checking out Gensim. They're really, really exhaustive suite of topic models. I'm a big fan of their work. So, and they're really easy to contribute to, great open source teams. So if, for example, you find out the seeding's not up to the standard of what you'd like to see, put up an issue and you could actually get someone to work on that as soon as possible as well. So if this interests you, just, yeah. But you can seed your topic models, yes. I saw another hand going up. I'm sorry, yes?
How do you choose the number of topics? Is there a rule of thumb?
Yeah, so the rule of thumb is, there is no rule of thumb really, but what you can do, for example, is you look at the size of your corpus. If there's 100 documents maybe, and you expect a certain number of topics, you would start with that number. Now, this is again really hand-wavy. If you want a particular way to choose your number of topics, there is a method called topic coherence. Topic coherence just tells you how much human sense do these topics make. So then what you do is you train 10 topic models on the same corpus with 10, 20, 30, 40, 50, 60, so how many ever topics you want. You train all of these models, then you check the topic coherence for each of these 10 models, and then you choose the number of topics with the highest number. So this is a quantitative way to figure out topic coherence. Honestly, when I'm doing it, I just wing it. I'm like, you know what, 7 topics sounds good, and then I just do bam, and it usually works out kind of. Yeah?
Yeah, I'm just wondering, like, if I have a product, let's say a towel, I have a lot of reviews. Suppose I have 5 reviews says it's clean, and another 5 reviews says not clean, and another 8 reviews says it's dirty.
Yeah, so in this particular case, things like sentiment or like semantics or like intelligent information is not what you're going to be getting. For example, you're not going to find out doing sentiment analysis of topic modeling, which is kind of what you're talking about, like clean, not clean. I mean, sentiment, you get the gist. So this is not something which is very useful because topic modeling only gives you words. One possible solution, when you're doing your bigrams, if not clean comes up often enough, not clean will actually be picked up as one bigram. So in this case, if you expect not clean to appear in your set, in your corpus, kind of force it to have not clean as one word.
But it can be not really clean or hardly clean.
Fair enough. So in this case, you don't get semantic information caught because you can see the results. It's literally just picking up the words. So, but then again, your topic will not be a dirty or clean topic. Your topic will be a towel topic. And this towel topic would have clean and dirty. So you see, that's not the purpose of what you want to do with topic modeling. If you want to find out the sentiment of the reviews, I mean, that's a whole other ballgame. We have sentiment analysis, and that's a completely different way you want to approach things. In that case, where semantics starts becoming more important, you'd use things like word2vec, which is a really popular machine learning algorithm, which I might talk about. I don't know if I have the time. But you'd use other techniques which involve meaning more. In this case, we're not really looking at meaning. We're just looking at a broad overview of our text. Yeah? Any other questions?
Well, I just actually I added the
Yeah?
stop words and ran it all again, but it's still there.
It's still there?
Same for prawn, so it's not going out. I didn't know why.
Okay. I'm sorry?
Function doesn't seem to remove now.
Okay, could you do me a favor? Could you just open an issue on the same repository, the personal my repository with this notebooks, stating the issue so that what I'm going to do is once I go back or tomorrow during the conference, I can play around with it and then update it, make the changes on the GitHub repository. So tomorrow, when you can actually log on, look at my GitHub repository, you can see the correct outputs. So just open an issue with the exact, but that should not be there, just to clarify.
It's the opposite. If I add it in my stop words, then it works.
Yeah?
But it retains all the other possible stop words if then.
No way, really?
Yeah.
Okay.
I got it. Yeah.
Okay, cool. Just again, like the more issues you folks open up, the better, so I can have more examples to look at, and then I can get this fixed, because I think I've seen this before, and my old tutorials don't have this problem. So just whatever issues you have with any particular lines of code, you can see. By the way, just another point which I forgot to mention. The notebook I'm running right now, it's called Text Analysis Tutorial Unrun, and then I'm running it. I have an already run version of the exact same notebook on the repository as well if you want to see the results, so you can compare. But if there's a mistake, I'm going to have to rerun both the notebooks. But thanks for pointing that out. Is there anything else? Okay. So now we're done with GenSim for now. I'd just like to talk about the other things that GenSim has to offer. Apart from topic modeling, it has something called dynamic topic modeling, which includes timestamps as well. So you can find out evolution of topics over time. It has summarization, so it has ways to summarize your text. It looks for sentences in your articles which have the most information, and it can create summaries of synopsises and things like that. It can do, pardon me, it can do word-to-vec. Word-to-vec, oh, I really like word-to-vec, so I'm just going to give you a small example. Though I'm pretty sure if you folks have been around various data science meetups, you would have heard word-to-vec come often. I'm just curious, does anyone not know what word-to-vec is? Oh, awesome, okay, cool. So word-to-vec, so like the name suggests, it stands for word to vector. So what it does is it basically creates a vector representation of a word. Do you know what a vector is? Yeah, so when we were creating a vector representation of a word, we'd want to try and have this vector try to best capture the semantic meaning of to capture the understanding of the word. So I'll give you an example. Normally, if you're representing the word, this is the most popular example used in Word2Vec, which is it's done by these folks at Google, and there is this really fun paper on it in 2013, so you can actually see the entire research paper, which is a really well-written paper. And the example they give is they calculate, so a vector, like I said, is basically a mathematical representation of a word. Now, if this mathematical representation of a word can also translate the meaning of the word, that would be really neat. And that's what Word2Vec does. Word2Vec understands the meaning of words and tries to show that in a mathematical way. For example, they did the word vector of king minus man plus woman. So again, just to make this clear, king minus man plus woman. Any guesses what that would be? I mean, come on, someone yell queen. No one's queen. Yes, thank you. So king minus man plus woman is queen. I mean, even as human beings, when we think of this intuitively, yeah, we get an idea of royalty, take out the man, add the woman, and you get queen. Now, the incredible thing was Word2Vec also actually did this. It actually, if you did the word vector of king minus the word vector of man plus the word vector of woman, the word vector which we got was closest to the word vector of queen, which is really, really neat. So this is an entire, there's a lot of different, these are called word embeddings because it captures semantic understanding of words. Now, there's a lot of different kinds of word embeddings, and GenSim has around 4 to 5 of these fast text, I think, point care embeddings, and Word2Vec, of course, different kinds of word embeddings. GenSim also has these, so I'd really recommend checking GenSim out if you're interested in text analysis in general. Topic modeling and word embeddings tend to be its specialty. What we're moving on to now is text classification. We're going to be using scikit-learn because scikit-learn has, GenSim doesn't have a clustering or classification algorithms, but scikit-learn does. And scikit-learn has a pretty decent text processing pipeline as well. So this is a really, really super vanilla example. I'm not even kidding. But it's just to kind of give you an example of the workflow of when you're dealing with clustering or classification. In this particular example, what we're going to be doing is we're not going to be using the Lee corpus data, the Lee background data set anymore because that was unlabeled. Remember, that's why I used it for topic modeling. It had no additional information. And we didn't have any idea what kind of classes are found in that corpus. In this corpus, however, which is called the 20 NG corpus, or the 20 newsgroup corpus, there's 20 different categories in our corpus. So we're going to be using an example of classification where we're going to pick up a document and then classify it in only 4, not 20, because I just want to show you what it looks like. And the 4 ones which we're going to be using are atheism, miscellaneous, graphics, and space. These are the 4 top categories which are on the scikit-learn website, which is why I chose these. Kind of lazy, I know, I'm sorry. But this is, again, like I said, to give you an example of the pipeline or the workflow we'll be using when we're dealing with clustering and classification. The difference between clustering and classification is in classification, we know our labels. We have our labels, and we want to put our documents into these labels. We're sure it's going to be in one of these labels. In clustering, we don't really know what the labels are. Even if we do, we just want to kind of generally put it somewhere in similar clusters. Classification, we're sure that it belongs to this or this or this or the other class. Here, 4 classes, like the ones you see over there. Again, let's be looking here. You can see the 4 categories over there. And let's start our imports. So over here, fetch 20 newsgroups fetches our data set, truncated SVD, TF, IDF, hashing, and all of these over here are used to pre-process our text data. I'm going to give a little more information about that, and it's the same with our pipelines. So let's see, I'm going to run this over here, and I'm going to explain what's going on. Data train, fetch 20 newsgroups. Again, as you can see, this is kind of self-explanatory. If you're not understanding any particular line over here, please stop me. But here, we're just picking up our training data. And so the thing about text processing is it's generally what we consider a high-dimensional problem. A high-dimensional problem is a problem where there's a lot of features. Now, what exactly are features? Features are any kind of information which we use to make a classification or make a decision. Here, our features are our words, yeah? Because we're going to be using words which are in the document to make decisions of which class does this document belong in. Is that clear? Now, assuming that in these 4 classes which I picked up, which are these 4 categories over here, there could be 10,000 words or 20,000 words, or I'm not sure about the exact size of the vocabulary, but either way, those are a lot of features. And we don't want to be using all of these features while making a decision. It just takes more time, and it's not the best way to do things. So what we're going to do is we're going to kind of shrink or reduce the dimensions of our data. The way we do this is here you see vectorizer is equal to TF, IDF vectorizer. What I mentioned before is last time we used bag of words, remember, where we kind of we built these bag of words using Jensen. Now we're going to use TF, IDF, which is just another way to represent these words. And after that, we're going to, so then we do vectorizer fit transform data train.data, which basically means over here, now we have our TF, IDF data. After TF-IDF, we're going to be using SVD, which stands for singular value decomposition. And what it does is it's basically linear algebra, and what it does is it reduces dimensions. I know that's a bad, it's probably not the reasoning which you wanted, but a little more, okay, I'm trying to see what would make an interesting way. So if you have a really, really massive matrix with all of your features, what kind of a smaller matrix can you construct using these documents, which represent these words in the best possible way using linear algebra? Again, I know, again, that sounds very hand-wavy. If you're interested about the actual mathematics, I'd recommend Googling it. But as of now, what we're going to be doing is using truncated SVD. Here we say number of components is 5, which means we're going to reduce our data set from how many ever number of features it was initially to just 5 components or 5 features. Yeah? And these are just the steps you do to create this pipeline and normalize our data. This is just what we're going to be doing to get our data ready. We're going to be doing the exact same thing with our testing data over here. And now let's do the actual classifying. So the first classifier we're going to be using is the naive Bayes. Is the naive Bayes? Yes, it is. The Gaussian naive Bayes. So the naive Bayes classifier, what naive Bayes pretty much does is it uses a Bayesian probability, which means that it's going to check what are the odds. For example, I'm going to give you an example of classifiers using spam. That's an easy example. You want to classify your textual data into spam and not spam. Yeah. So it's likely that certain documents are going to contain words which are are going to put it more likely to be in spam. For example, winner or enlargement. Or words, if they appear in your mail, they're likely going to be spam. So this means that if these words appear in our documents, higher probability this belongs to spam. So it's just based on conditional probability. This is what naive Bayes does. And it's super easy to use it. We're going to G and B is equal to Gaussian naive Bayes, which is just a Gaussian version of the naive Bayes algorithm. And Y pred, okay, so now that this is done, so ypred, now what you do is gnb.fit train x and y. So what you're doing is you're training your classifier, which is a naive Bayes classifier, with your training data, which is your x and your y. Your x are your documents, and your Y is which class it belongs in. So this is the information you're giving your classifier. All my documents, and which class do these documents belong in. It then creates these probabilities, which I talked about, these conditional probabilities, and then we predict with our test data. So in just one line of code, we have Y, so YPred NB now has every single class of every document in our testing. So for example, I want to create a new, yeah. So let's look at, so this tells us that in X test, the first document belongs in category 0, then 3, and so on and so forth. So what's going on right now is YPred NB contains, after we fit our GNB model using our training data, we then predicted on our testing data, the results are stored in YPred, and these are the classes of our documents. Is this extremely clear to everyone here? Yeah? Awesome. So now we're going to move on to another kind of classifier. It's the SVM classifier, which is a support vector machine. It's a bit more difficult to explain this conceptually, but what support vector machines does is, normally if you have a lot of data, we try to draw a line to classify our data into two different categories. And SVM kind of uses kernels to move to a different prediction space, and we try and drop a plane instead of a line to separate our classes. It's just a different mathematical way to actually do our classification. Again, if you want to get into the nitty-gritties of it, you can search up the details, but scikit-learn, luckily enough for us, is very, very well done and very well written. We can use these classifying objects as black boxes where we expect it to kind of work. If you want to get into more detail about which classifier is the best, that's a whole different ballgame. But I just wanted to introduce you all to the world of scikit-learn and classification using scikit-learn. So is everyone clear on where scikit-learn and text come into our whole pipeline of text analysis? Any questions regarding this particular section? No? Cool. We're now going to move on to, so just a point which you might have seen throughout this tutorial is, again, I'm not going into a lot of depth into either topic modeling or computational linguistics or classification. I'm just giving you an example of the fun things you can do with text. What I've done is given you the links to actually go into more detail if you're interested in this particular aspect of text analysis. Yeah? Now, this is our last part, at least in this tutorial. So what we'll be doing is generating text. I talked earlier about the example of generating Shakespeare text, where we try and create make a machine create this kind of text. I'm going to give you a little bit of an intuitive example of how neural networks do this. It's quite complex the way they work. I've put two links over there which I really, really enjoy. Understanding LSTM networks and the unreasonable effectiveness of recurrent neural networks, which are two very, very popular and a lot of fun, actually. Like, I'm not even kidding, like, loads of fun, both of these blog posts. They really get into the details of how these work and give nice intuitive examples. So if you want to get more into how these really work, you can read these articles. I've linked to both of them in my directory. To give you a bit of intuitive understanding of how neural networks allow us to generate text, it creates a window and tries to, say you have a document. What it does is it first reads your entire document a whole bunch of times, and it tries to predict, given this character or a word, depending on what kind of neural network it is, if it's a character level or a word level, it says, based on this character or word appearing right here, what are the odds, what is the most likely next character appearing somewhere? So given the word, for example, the quick brown fox jumped over the lazy dog. So in that particular example, if you keep telling a neural network this sentence, it's just going to say, given the quick brown fox, it's going to predict the word jumped next, because it's just seen that so many times. Now, you go on and train this over a really, really massive corpus. It starts to learn or pick up or understand what kind of words do I need to start predicting so that it mimics the original distribution the best possible way. So what's going to happen is soon you're going to have a neural network which is going to be saying things, which is going to start talking. For example, there's a really fun example where there's a Trump tweet generator, where it kind of just generates tweets which it learns the way Trump says. When he says sad or big news or fake news, it can predict that. In fact, Vincent's, the PyData Amsterdam organizer here, who I suppose you all have met, has a really nice experiment where he generates Pokemon names as well. I really enjoyed that talk. Yeah. So this is an example of using neural networks to generate text. You can actually, so what it tries to learn is what are the odds of this particular style of language appearing based on the context. Now again, this is again super hand-wavy. So if you want to find out more about how this is done, check the links out. As for what we're going to be using to do this, actually generate text, is Keras. Keras is a really high-level neural networks library, which means that there are other libraries like TensorFlow and Theano, which allow you to actually construct your neural networks from scratch, where you choose what activation functions, how many layers, how many networks. But if you couldn't care enough about the actual insights of what's going on, and you want to create a neural network in really less lines of code, this is a really, really neat way to do it. So I would really recommend checking out Keras. Keras is actually built on TensorFlow and Theano, so you're actually using these libraries to build our neural networks, but Keras makes the layer of abstraction one level higher, making it easier for us to use. It's also right now one of the most popular neural network creating libraries which we have out there, and for text processing, it's really easy to do things. I'd like to note one thing. Most of the text here is, most of the cells over here are taken from the Jupyter notebook from my good pal Kirit, and he's done a similar tutorial as well where he focuses more into the details. Since I've talked about a lot of things before this, I'm not going to talk so much about the nature of all of the code over here. I'm going to, of course, briefly explain it, but I would highly recommend checking out that GitHub repository as well if you're interested about how exactly why we're writing these lines of code, though I'm still going to go over some details. So let's start with our imports. So what's going on over here is another example of how I told you before of how I mentioned computers don't understand text the way we do. So we're not going to have just words, right? So we need what this is called one-hot encoding, which is kind of saying 0 is if that word exists, 1 if that word doesn't exist. So this is just an example of the kind of input data which our neural network needs. This is our Keras model now. So let's go into a little more detail about what's going on over here. So these are parameters of our neural network, which is things like drop rate, activation, and mode, which tells us what kind of characters we want to give our neural network. Now, it's been found out for generating text that these particular parameters are the ones which make it function for generating text better. If you want these neural networks to do something else, like classification, because you can also classify text with using neural networks, you'd be generating or constructing your neural network in a different way with different architectures, different kinds of layers, and different kinds of parameters. The parameters which you'll be using in this particular set of examples are just the best ones for text generation. So over here, our inputs is, of course, mind you, we are not, these are just functions. We're going to actually be running these functions later. But just to give you an example over here, this is the input shape. LSTM stands for long short-term memory. And what it does is, again, its architecture best allows us to capture the context which we need when we're generating text. It's not, for example, we need to remember what came before and also what's immediately around it. Like I mentioned before, this particular blog is super cool for understanding LSTM networks in particular, and LSTMs are really useful when we're generating text. Now we're going to be creating our models. Again, I'm aware of the fact this is really hand-wavy and I'm not getting into details. It's because we're running out of time, and I'd rather want to just give you an intuitive idea of how we're going to be generating this. But if any one of you still want to know what this particular line does, please stop me. So here we'll be using a sequential kind of model. That is the kind of model or the kind of neural network model which we'll be using to generate our text. And our model here is an LSTM, and hidden dimensions and input shapes are our inputs. Depending on the number of layers, again, the number of layers is simply the kind of complexity we will be having in our neural network. So this is for creating our model. Training our model is, so here loss, categorical cross entropy is just the kind of loss. What loss means over here is we want to see how, when we want to see how well our neural network performs, we check the loss. Loss is the difference between the real and the expected value. There are different ways to calculate the loss, and this is what we choose. Opt is your optimizer, which is just the way you want the neural network to do its optimization. There's also something called dropout rate, which helps when we tell our neural network to stop focusing or training on this particular thing, to drop out. It's to prevent something called overfitting. Overfitting is when we overgeneralize for a particular data set and it stops being general purpose. So again, these are all parameters which are involved in neural networks. I'm sorry for not getting into the details. If this was a deep learning tutorial, I really would have loved to. But in this case, I just want to give you enough context so you can later go ahead and do this stuff yourself. This is our, so until now what we've done is we've just created our model. We've not actually started the process of text generation. So I'm going to give a little bit of example, a little bit of context or intuition about how we can generate text. Once we create our model now kind of has an intuitive understanding of, given this particular character, what is the character most likely which is going to appear next. So we also want to, when we want to start generating text, we want to seed our model, like we talked about seeding before. Seeding means kind of giving it a kickstart or a push, and then after that it starts generating text. So over here we have our seed, and we have our start, which is going to be a random start. These are the loss and the optimizer we talked about before. And did I hear something? Yes?
Does seeding different from training?
I'm sorry?
Does seeding different from training?
Yes, seeding is definitely different from training. So what's training is when we are looking at our text and just figuring out our probabilities of what are the odds of the next word appearing. Yeah? What seeding is we give a word and then we're telling our model start. So seeding is kind of the first word we're giving our model after it's been trained. You see? Yeah? So what's going on over here is this is our, we only want to generate 250 characters for now, mainly because we don't have time and the training process takes quite a while. So this is the way we do it. We first predict, when we do model.predict, it basically means what is the next word which is going to come up. Then after that, we convert that, when we're doing np.argmax for prediction, we're choosing the highest probability, the word with the highest probability of appearing next, the character, and then after that, we are printing this. You're going to be seeing this over here. Now, what data I'm using over here is the same Lee background corpus, which we talked about before. So these are just, this is important information for the neural network when we are generating text, because we need, again, our IDs, which we talked about before, to recreate our characters. Again, this is more stuff to get our data. Oh, oops. What the? I'm sorry about that. There we go. So again, this is just getting our data in shape, making sure everything's good to go. And now we're going to actually do the heavy lifting, which is creating our model using the create model method, which we wrote over here, which I kind of walked you folks over. Now we're going to be training here. Remember, we're not doing any seeding yet over here. This is the part which is going to take some time. So I'm actually going to use this time to sum up and show you what the results are supposed to look like. So after we're training our model, epoch is just basically the training section. This is the already run Jupyter. It takes a little more time for us to actually do the training. Over here, what's happening is once we've trained our model, we're going to start generating our text. So you can see over here that it has been developing tools to something prison. It's the word Australia somewhere here. It'll be really nice. Oil prices, okay. Which means that we kind of recreated 250 characters of a newspaper article from the trainings that we trained on. Now, if this looks lousy, it's also because it was a really, really small data source. We didn't have much text which we fed to our neural network model, and we also spent very less time in doing the actual training. If you want it to be extremely coherent, you'd be training it more, and it takes a lot of time, hours, or even days to have a model which is generating text which is really, really human intelligible. What I would, again, really want you to do, and I cannot recommend this enough, is to read this blog post, The Unreasonable Effectiveness of Recurrent Neural Networks, which has extremely interesting examples from RNNs trained on different kinds of data sources and the results. It also has a Shakespeare example, which ends up being quite cool. It has, and this is really, really fun, it has an entire example trained on the Linux source code. So it's generating source code with correct braces and indentation. It's mental. So I would really recommend, super fun. So I would really, really recommend checking out that blog post. What I showed you here, you can actually put in whatever. So there's one particular line over here where I feed in my data source. I had a Game of Thrones one, but I kind of lost my data source, which would have been fun to show you folks. But so instead I'm using the boring 2001 newspaper corpus. But yeah, you can just replace these lines of code, and you now have text generated in the style of whatever you want. The blog post, again, has a lot more interesting examples. But as you can see, the code is also fairly straightforward. To understand if you want to make a better Keras model, you'd have to go more into the documentation of Keras and look at all the examples. But there you go. These lines of code, let's see if our model's been trained. Any wagers? OK, it has. And now we're going to... Come on, don't do this to me. There we go. Yeah, so Afghanistan, something, yeah. So you have oh, incinerator, that's kind of harsh. Okay, so yeah, so this is the text generated in the by the neural network, which was trained while we were talking. That barely took any time, which is really neat. Now, if this happened in around a minute, you can only imagine with a much larger corpus and with more concentrated training efforts that we're going to be seeing a lot more sophisticated kind of outputs. So yeah, that brings us to the end of this tutorial. We talked about a lot of different things, and that was the purpose of this. It was not to go into depth behind any one particular kind of text analysis technique, but to rather explore the giant, the scope. There's just so much. If we do a quick recap, we started out about why NLTK is horrible. Sorry, I know this is recorded. Oops. So we talked about why you shouldn't use NLTK, and then we talked about why you should use Spacey, because it does a whole bunch of things in one shot. Then we talked about different ways we get our text ready by creating bigrams in New York and so on and so forth. We talked about dictionaries and corpuses and basically entire training part. We talked about computational linguistics, which is about parts of speech tagging, NER, dependency parsing, which is, again, what Spacey does. Then we moved on to topic models and how we can find an overall view of our text using topic models. After that, we talked about text classification using scikit-learn and how we can set up our data and how classification works when we know our classes before we start our experiment. And then after that, we did deep learning, where we're using neural networks to generate text. I also briefly talked about Word2Vec, though I didn't actually show you any Word2Vec examples. It's actually really, really easy code in GenSim as well. So I hope you're all thoroughly impressed enough with text analysis and Python. Most of this is native Python, and all of these libraries have really nice communities, really friendly people, and I would really recommend checking these libraries out, checking out text analysis in general. Also, since I'm here, a little bit of publicity. I've written a book on text analysis, like 2 weeks ago, and it's going to be out. It's published by Pact Publishing House. It'll be on Amazon, and I think I'm going to add the link to this repository so you can find it later. The book pretty much covers all the things I talked about, and more, of course, with a lot of details, and Jupyter notebooks and text examples. So yeah, so you can buy my book if you like text analysis. And is there anything else? Questions? And I'm here at Amsterdam for PyData today and tomorrow and day after as well. So I'd love to hear your questions and raise your issues on the GitHub repository. If there's any problems with the code, I will do my best to look at it and push the updates so that you can have the final working code as well. I would have liked all of you to actually run the notebooks yourself. That's what I normally like to do in these tutorials, but couldn't happen this time. But I hope you all still had fun. Thank you for having me.